Um, so what I'm going to be talking about now are piecewise functions. And why are we interested in piecewise functions? Well, we have a relationship between y and x, the independent variable and the dependent variable. And usually this relationship is determined by some function f of x. And when we usually work with functions, often in calculus, we're dealing with one relationship. There's some f of x where we put in inputs x and it kicks out inputs y. But sometimes this relationship could suddenly change. And to accommodate that possibility, we have this technique called piecewise functions. Let me illustrate. Let's say you have a friend and you get to know each other over time, and we call that familiarity. And as you get to know each other, hopefully you get along. So you meet each other, and the relationships, you get along, you're doing all right. It's about the same. As familiarity increases, you might discover some differences of opinion, though. And some of these differences are going to make the relationship become, well, you're not going to get along as much. But then you'll discover you have opinions that you share in common. You're like, oh, this is great. And then you discover you have opinions that are very different, and you wonder if we're going to be getting along at all for much longer. But then you discover that, well, you know, these differences of opinion, they're different points of view, and it invites you to see the world from another perspective and maybe kind of adds to your experience. So you start to get along really well once you discover these differences of opinion are, well, they're very positive for yourselves and your relationship. So here's the point. You start out, pretty consistent friendship. And then you kind of hit sort of a rocky phase. Sometimes it's up, sometimes it's down. And then you discover that these differences of opinion, well, they actually show you a lot about life that you wouldn't have imagined. And so you discover that your differences are actually strengths. And so the relationship becomes very fruitful. So the point is, the relationship between getting along and how well you know each other, this changes sometimes rather suddenly. Go through different phases. And so this is the idea of piecewise functions. Let me give you another example. Let's say you're looking at the price of a stock. Well, let's say this stock at 10 a.m. has a price of $2. And it's going to stay that way all the way until you get to 12 p.m. And then suddenly the price of the stock increases to $5. So at 12 p.m., it's no longer $2. It's now suddenly $5. So what this says, and the stock starts at $2, if you were to purchase this stock at any time before 12 p.m., it would still be $2. But the second you have the strike of 12 p.m., the stock is now $5. And then it's going to be that way. It'll stay at $5 And then suddenly, right at the strike of 2 p.m., it's going to be $3. So at 2 p.m., it's no longer going to be $5. Now going to be $3. And then it continues on. So again, this is the idea of a piecewise function. We have different behaviors or different relationships between price and time. From 10 a.m. to any time before 12 p.m., the relationship between price and time is going to be $2. That's how much this stock costs. Then suddenly, right at the nanosecond strike of 12 p.m., you're going to get a jump in price to $5. And then if you try to purchase this stock at any time before 2 p.m., it's going to still be $5. And then suddenly, at the exact moment of 2 p.m., the price drops down to $3, and then that's going to be the price of the stock until the market closes. So when you have these drastic changes in the relationship between price and time, we're going to get a graph like this. And this is a piecewise function. Now, it's still a function, even though it has these different phases. But it's still a function because it passes the vertical line test. Intersect at only one point. Intersect at only one point. And here, this is hollow because exactly at 12 p.m., this stock is no longer $2. So there's a hole at 12 p.m. and $2. The price jumps up to 5. So this is an empty point. This is a filled point. We only intersect one filled point. So that means we're still a function. So that's kind of the idea of piecewise functions. That sometimes the relationship between x and y can suddenly enter a new phase. And we want to come up with a graph or a picture of how all these phases fit together. So I'm going to go over some examples of what these piecewise functions look like when we try to graph them and some considerations that we want to have. So first example. Let's say we have something like this. Well, here the relationship between f of x and x goes through 3 different phases. When x is less than 0, the relationship is going to be a parabola, x squared. But then when we get to the phase where x is between 0 and 2, the relationship suddenly changes. We now have x plus 1, a line. And then once we get to the final phase, where x is greater than or equal to 2, we have a constant line for e. So let's take a look at this. Let's take a look at where our phases are changing. So we have a change at 0. And then we have a change at 2. Now, we can divide this our graph into these 3 phases. First phase, x less than 0. Second phase, x between 0 and 2. Third phase, x bigger than 2. So let's put this together. When x is less than 0 in our first phase, so here we go. The relationship between x and f of x is x squared. So that means this is a parabola, and it looks something like this. So that's our first phase. Now for a second phase. Now, there's something we want to keep in mind. When we get to the boundaries of our phases, we want to know, we want to definitely figure out where these different functions, or these phase functions we see in the phases, where they contact or they intersect the boundaries of the phases. So this parabola, when it reaches the boundary between the first and second phase, it's down here at the origin. Now we're going to look at this line in the second phase. So where is it along this boundary? Well, we can figure that out by substituting in x is 0, because the boundary is at x is 0. So 0 plus 1, that gives us 1. So that means for the beginning of the second phase, we're going to start up here at 1. Now, there's something else we want to keep in mind too, is should we have a closed dot or an open dot, and we'll get to that. But to start the second phase, we're going to start at x is 0, and we're going to have a y value of 1. Now, x plus 1 does something sort of like this. And then we're going to get to the boundary between the second phase and the third phase. So what is this doing at the boundary? Well, the boundary is at x equals 2. So if we plug in x is 2, add 1, we're going to get 3. So we're going to stop at x is 2, y is 3. Now, we go to the third phase. Now, the third phase says that we have a constant function, f of x equals 3. So that means we start at 3, and then we just continue on. Now, we want to take a look at these boundaries. We have a gap here. Now, should this be an open dot or closed dot? Should this be an open dot or closed dot? Well, we're told for the first phase that x is less than 0. In other words, it never actually gets to be 0. So at x is 0, we have an open dot. Now, if we take a look at the second phase, though, and that's this line. This line describes the relationship in the second phase. We do see that in the second phase, x does get to be 0. So that means we have a closed dot. Now let's take a look at the boundary between the second and third phase. Well, if we look at the end of the second phase, it doesn't let x be equal to 2. So that would technically be an open dot for the end of our second phase. But we look at the third phase. The third phase says x can be 2. So at the beginning of the third phase, we use a closed dot. But because this open dot and closed dot overlap, closed dot fills it in. So this is what we've got. For the first phase and the relationship between x and y, the relationship is a parabola. And there's going to be a gap, an open dot here at x is 0. But then in the second phase, the relationship changes. Now it's going to be this line starting from x is 0, y is 1, slanting up to x is 2, y is 3. And then the relationship changes again, and now it's a constant relationship. So that's how we can graph these piecewise functions. Let me do another one. So let's say this is our piecewise function. This function has two phases. There's a 1 over x phase, and then there's an x phase. Where do these phases occur? Well, the 1 over x is when x is less than 0. And then the relationship that's just x, or the identity function, this is for x greater than or equal to 0. So let's put in our graph. We'll put in the boundary between our phases. For the two phases, the boundary appears to be 0. So phase 1, x less than 0. Well, this is 1 over x. So what we want to do is we want to graph 1 over x, or the part of 1 over x, when x is less than 0. Now, 1 over x is a function that does something like this. But we only want the part when x is less than 0. So that means for the first phase, the relationship between x and y is going to look like this. All right. So now the second phase. X greater than or equal to 0. Now, keep in mind that we allow x to equal 0. So the function x, the identity function, looks something like this. And since x is allowed to equal 0, I want to make sure we put a dot there. And so this is our piecewise function. The relationship between g and x, or this is functioning as our y variable, y and x. It starts out like this, whenever the x is less than 0, and then the relationship enters a different phase, and then it continues on like this when x is greater than or equal to 0. Now, you might be wondering about an open circle here. Shouldn't there be one? This is a vertical asymptote for y equals 1 over x. And so as you get closer and closer to 0, you can get as close to 0 as you want. You'll never quite get there, and you'll just keep dropping farther and farther down. So we don't have to worry about an open circle in this case. There's a vertical asymptote that's not going to let us get to 0 anyway. All right. So let's take a look at this. So let's say we have something like this. Well, again, let's take a look at our phases. Now, the first phase are all the values of x less than 1 or equal to 1. And then the second phase will be all the x values greater than 1. So our first phase is here. Our second phase is over here. So let's take a look at this. We've got to graph this. Now, if you have a graphing calculator, this is easy to do. But if you don't have a graphing calculator, you can do this. Start out with x squared. Now, x squared looks something like that. Now, let's take a look at negative x squared. that will just flip that parabola down. And finally, we could add 4. And that's going to be the same as 4 minus x squared. So when we add 4, we're going to raise that parabola up 4 units. So we're going to get something like this. Now, there's usually 3 things that you want to know about a parabola. No, we'll say 2. We usually want to know the vertex, and then we want to know where it crosses the x-axis, or where this thing is equal to 0. So let's figure that out. Where does this thing cross the x-axis? So to do that, we're going to set our parabola equal to 0. Solve for x squared. We can solve for x. So this is what we're going to find out about a parabola. The vertex is going to be 0, 4. Then it crosses the x-axis. And x is negative 2, and x is positive 2. So let's go back to our graph. Here's our vertex. Here's where we cross the x-axis. And we're going to cross the x-axis here, but that's in phase 2. We're not supposed to go into phase 2. We're supposed to be limited to phase 1. So we can do this. Roughly speaking, something like that. But now what we want to do, we want to determine where this thing hits our boundary. Now the boundary is at x equals 1. So we got to substitute in x is 1 to find out the y value of where we reach this boundary. So it's going to be 3. So that means we're going to hit the boundary right here. And let's take a look at this. Phase 1, we're allowed to equal 1. So we can put a dot. And so that's how we do phase 1. Now we're going to do phase 2. So we need to graph this parabola. Well, because the lead term is positive, we know that this parabola is going to be upward facing. And that's just a thing with parabolas to keep in mind. If the lead term is positive, you have an upward facing parabola. If the lead term is negative, it's going to be downward facing. So again, we want to figure out where this thing intersects the x-axis. So we'll take x squared plus 2x, set it equal to 0. Now it's tempting to want to divide by x. With this, you actually want to factor. First off, x could be 0. So if you're dividing by x and you're allowing x to be 0, you get a division by 0. But also, if we divide by x, we're going to lose one of our values. We're going to lose one of the locations where this function crosses the x-axis. So if we factor this, now we ask this question: when is this equal to 0? Well, it's going to be equal to 0 whenever this is 0 or whenever this is 0. Because if this is 0, 0 times, well, any number will equal 0. Likewise, if this is 0, 0 times any number will be 0. This is 0, of course, when x is 0. This will be 0 when x is -2. -2 plus 2 is 0. So this is going to cross the x-axis at these two locations. Now, if we take a look at this, though, x is -2 and x is 0. This is in phase 1. So this isn't really going to be part of our graph. We don't have to graph this part. We only need to graph the part in phase 2. So it looks like where we cross the x-axis, we're not going to have to worry about that. But we do want to try to find the vertex. So it might have been a while since you've done this, but for a parabola of this form, the vertex has an x-coordinate of -b over 2a. And then the y-coordinate will be f of -b over 2a. We take the x value and we put it back into the parabola to get our y value. So that being the case, what's our -b over 2a? Well, let's take a look at our parabola. We have x squared plus 2x is equal to our f of x in this phase 2. Now you can rewrite this, though, as 1x squared plus 2x plus 0 is f of x. Where in this case, this is our a, this is our b, and that's our c. So we need an x of -b over 2a. So in that case, this will be -2 over 2 times 1. And that'll come out to -1. So the x-coordinate is going to be -1. All right. Well, we could come up with the y-coordinate, but the problem with that is we're still dealing with something that's in that phase 1. So we don't need to worry about it. So this is interesting. We don't have to worry about where this thing crosses the x-axis. We don't have to worry about the vertex, because those all are occurring in phase 2. Phase 1. And phase 1 is dominated by this parabola. The second parabola, only we want the part that's in phase 2. So this is what we're going to do. Because this is positive, this lead term, the term that has the x squared attached to it, is positive, we know this is facing upward. And again, if it's negative, it'd be facing downward. So let's just take the fact that we know that the boundary is going to be 1. And let's find the value of this at x equals 1. Now, it's going to be an open circle. But what we're going to know is where this thing tries to start. And then, because it's upward facing, we know kind of what its behavior is going to be. I'm going to make a note that the vertex occurs at x equals -1. And I'll show you why in a little bit. So we have f of x, x squared plus 2x. So f of 1. 1 squared plus 2 times 1, and that's going to be 3. So this thing's going to start at 3, right where phase 1 ends, or y equals 3, I should say. Now here's the thing. The vertex for this parabola is at -1. And we know that this thing's going to be facing upward. So that means the vertex is going to be doing something like this. So the phase 2 part of this parabola is going to be the part doing that. While the part that's doing this is going to be to the left of that vertex at -1. So what we're going to get is something kind of like that. Very rough sketch. Now, we're not equal to 1, but we start, you know, the open dot here for phase 2, it's filled in by where we stop for phase 1. So this becomes a solid dot in the end. And that's going to be it. And so that's the graph of our piecewise function. We have 2 phases. We have this first phase, which is the relationship between f and x, is this parabola. And then the second phase, the relationship changes to that parabola. So let's take a look at one more of these. And this is probably the most famous piecewise function you encounter, at least in algebra. Is the absolute value of x. So the way this works, the absolute value of x makes everything positive. So if you're x and you're less than 0, we got to make you positive. So we multiply by a -1, or we put the opposite operator, which makes negatives positive and positive negative. So if a negative number with a negative will become positive. And then if you're already positive, well, you just stay the same. And there you go. So as we graph this, again, our boundary here between, we have 2 phases. Phase 1, x less than 0. Phase 2, x greater than or equal to 0. So for phase 1, we use the negative x function, which is the identity function, except sloping downward, but it continues on in that direction. And it's going to be an open dot because we're not allowed to equal 0. And then for this one, we get into phase 2, we can equal 0. So we fill this in with a closed dot, and we continue on with the identity function. And so this becomes the graph of the absolute value of x. So formulas. Let's say you have this. Let's say you have something like this. Well, what we seem to have here are 2 phases of the relationship between x and f of x. And it looks like the phases have a boundary at x equals 1. We could call the first phase x between 0 and 1, because we start at 0. We're going to include 0. And we go to 1. And we could have said this equal to 1, but we could do less than 1. That's fine. The second phase, we have 1 less than or equal to x, less than or equal to 2. So we do want to make sure we do get a closed dot at 1. So we're going to do that here. And then we have a closed dot at 2, so we better have that there. So these are our two phases. So what function is here and what function is here? Well, here, this phase of the relationship, we have a line going from 0, 0 to 1 and 1. And you can use different formulas to figure this out. For example, to figure the slope of this, well, what we can do, call that 0, 0. And we can use our slope formula to come up with the slope. Now, you might also recognize this is the identity function. But let's say you didn't do that. Well, in that case, y2 is 1, y1 is 0. x2 is 1, x1 is 0. And what you're going to get, 1 over 1, or a slope of 1. Now, we also can note that the y-intercept is 0 and 0. So if we go to y equals mx plus b, or a slope m is 1, and the y-intercept, or the y-coordinate here, that's going to be 0, or y is just plain x. So that's the first phase of this function. So we need the second phase. And again, the coordinate here, we're going to need this. The coordinates of that point are 2 and 0. And we can call this x1, y1 also. So the slope, we'll get something like this. Double check that real quick. Looks good. Looks good. And so we're going to get a slope of -1. Now, we do kind of need to think about this one because we don't have a y-intercept. So what we can do, we can use the point slope formula. And that's going to give us the formula for this line. Now, the point slope formula is this. Now, we have x1 and y1 picked out already, so we can use these for the x1 and y1 in the formula. And then we have the slope -1. So we got something like this, or y is -x plus 2. And so that's going to be the relationship in phase 2. And so this will be our final answer. All right. So that's going to be the introduction to piecewise functions. I'm going to do a second part to this video in just a little bit, and then I'll get that posted as soon as possible.